Hello guys, welcome back to our channel. Today we are going to see what is a ripple carry adder and how to make the Villa code for this ripple carry adder. A ripple carry adder is nothing but an extension of the full adder. By using the full adder, we can perform only the 1 bit operation with the 3 inputs. But in the ripple carry adder, we can perform n bit addition operation, and it can also work as a parallel adder. This ripple carry adder can be formed by arranging the full adder blocks in the sequentially. That means suppose today we will construct a 4-bit ripple carry adder. A 4-bit ripple carry adder. So for that, for a single bit ripple carry adder, we require a single bit full adder. So in the case of 4-bit ripple carry adder, then we require a 4-bit ripple carry adders. I mean a 4-bit full adders. So for that, I am considering a full adder blocks. I'm considering as a F as a FA0. F is FM means nothing but the full adder. FA1 full adder 1, and next full adder 2 and full adder 3. That means we can perform 4-bit addition operation at a time. That means this ripple carry adder will consist of a 4 inputs. That means A0, B0, A1, B1, A2, B2, A3 and B3. Right? Here Cn is the input, and for every full adder we have a carry input. The carry will be propagated from one block to another block. That's why this name is called ripple carry adder. Ripple carry adder means nothing but the carry will propagate from one block to another block, is nothing but the ripple carry adder. So that means here some S0 will be generated and the carry C1 will be generated, and it will be given to the next full adder block. Here the sum S1 will be generated, and here the carry C2 will be generated and given to the full adder, second full adder, and here the sum S2 will be generated and the carry C3 will be given to the full adder 3, and here the final sum S3 will be generated and the final carry will be given. So these are the final outputs of the 4-bit ripple carry adder. For example, if we have a 4-bit means we have 4 numbers. If A is equal to 0 0 0 1 and B is equal to 0 0 1 0, that means it is 1 and it is 2. So adding this 1 1 0 0, here 3. In this way the 4-bit operation will be done. So I hope this ripple carry adder is understand by you. Okay, in order to design a 4-bit ripple carry adder, we require 4 full adders. So for that, firstly we have to define the full adder block. So for that, I am going to define the full adder first with the name called full adder. We require for full adder we require 3 inputs A comma B comma C, and we require a 2 outputs, nothing but sum comma carry. Here we have to assign the operations for sum and the carry. For sum, operation nothing but the A XOR B XOR C. For carry, the expression nothing but AB means A into logical and into B plus B into C and C into A. Here we have defined the module full adder, and I am ending this module. Now for our ripple carry adder, the full adder block is ready. Now we have to define the ripple carry adder. So for that, I am going to define the ripple carry adder with the name called RCA. RCA is nothing but the ripple carry adder. So I am going to define the ripple carry adder, and we are going to design the 4-bit full adder, right? So I am giving the syntax, right, like 3 is to 0, which is nothing but we are going to design 4-bit triple carry adder, right? So we 0 1 2 3, in this way this syntax will be done. If you want to design 8-bit, then 0 is to 7. If you want to design 16-bit, then the syntax will be 0 is to 15, in this way. So inputs are nothing but a comma b, and another one is the input c. And in the same way, output also 3 is to 0, because we are giving 4 inputs and we are getting the 4 values as a sum. So 4 sum, and output is nothing but carry. Okay, we given the all the inputs and outputs required to our triple carry adder. Then we require a bytes, because the carry will be propagated from the one block to another block. So if we have 4 blocks, then we require three carries in between the blocks will be propagated. So for that, c1, c2, and c3. And now I am assigning the operation. I am calling the full adder function full adder, and I am giving as a fa0 for the first one, a0, that means a of the initial bit 0, comma b of 0, comma c, comma s of sum of 0. The sum is nothing but the output, and here the carry. That is the final one, right? Here we will get the c1. Okay, I'm just copying this line and I will continuing this. Now, and next we will call as the first block full adder one. Wait, fa0, and I'm giving the next a1 bit b1, and the sum will be 1. And the in the first block, the c1 will be given to the second block. So it is this c1, and the carry will be c2. And next block, which is nothing but the second block, I mean third block, here we will give the second bit 2, and here the c2, and the sum will be 2, and the carry now we will get this c3. And this is the final block, which is nothing but the fourth block, fa3, and we are giving the third bit, and we will here the c3 will be given, and the sum is the 3, which is nothing but the final sum, and here carry, which is our the final output. Here I am closing the end module. This is the design code for our RCA. Now we have to write the test bench to verify this functionality. So for that, I am going to define the module with the name called TV, and inputs are nothing but the register 3 is to 0, a comma b. The other inputs are C. Outputs are nothing but 3 is to 0, sum, another one, and finally is the wire carry. Here now we have to define the syntax as a, we have to give all the inputs which we used in our module carry. Yes, I am now I am going to give starting the test bench initial begin, and we have to write the dump file command to get the output file, file.vcd, and dollar dump files. Now I am going to give the our inputs. Initially I am giving the cin is 0, and a is equal to, which is nothing but a 4 bits, right? So 4b 0 0 0 1, and I am just giving the random bits 0 0, sorry, 4b 0 0 1 0. I am giving some time delay, and now I am going to give some other bits 4b 0 0 1 0, and b is equal to for of b 10110, and I'm giving the another time delay. Just these two inputs are currently sufficient to verify this ripple carry is working or not. So I'm ending this block with a command called $finish, and I am ending this module. Okay, this is the distribution code for our module to verify the functionality, and this is the design code. Now I'm going to select the tools and the simulators, which are nothing but IQRS 0.9.7, and open EPU after the run. And I'm going to save this file, and I'm going to run this file. And before that, we have to give the name for the file, right? Okay, here I'm giving the RCA, and I'm going to save this file again, and I will again run this file. As the file is running, let's see whether there are any errors in the code. Yes, there is some error called module TB in the distribution SB.12. Sorry, here the input is nothing but the C, but I given C, so this is the error in this code. Now I'm going to run this file. Yes, the output is came. As you can see that here we are given the inputs as first initially 1 and the 2. 1 and 2 is another relation between the 1 and 2 is the 3. And here you can see that one input is 2 and another input is 10, but it is showing in the hexadecimal, right? So in the hexadecimal the 10 form will be A, so 2 plus A, I mean 10 plus 2 12, 12 the representation is C. So in this way the ripple carry will be work. And thank you for watching this video. If you have any doubts, please mention in the comments, and stay tuned for the next video.